Hello there and welcome back to the channel. Today is July 18, 2025, a lovely Friday. And you know what that means. It's time to pull another trending article from the archives and see what's cooking. And your host, Nino-Ani. And today we've got a real brain tackler for you. It's one of those papers with a title that's, a bit of a marathon. You ready for this? The title is Modal Analysis and Multimode Waveguides based on Large Step Size AdaMax from Far-Field Amplitudes. The quote is Fixed Waveguide all 7,007.12,209 milliwatt. It's long. Okay, so what on earth does that even mean? Let's break it down. That's actually way cooler than it sounds, I promise. So imagine you have a bike. But instead of water, this bike carries waves. Like light for fiber optics and microwaves for communications. That's basically a waveguide. Now these pipes are often multimode, which means they can carry multiple signals, or modes, all at once. Think of it like a highway with many lanes of traffic. The problem, the big challenge this paper is trying to solve, is that these different lanes of wave traffic can get messy. They interfere with each other. They can cause power loss, and they can mess up the signal quality. It's like all the cars suddenly trying to swerve into each other's lanes. Tech is a see. So, scientists need to do something called modal analysis. That's just a fancy way of saying they need to figure out exactly what each wave, each mode, is doing inside that pipe. We need to know its power, which is like its volume, and its phase, which is kind of like its timing relative to the other waves. But I patch. The old ways of doing this are kind of bad. Some methods involve literally sticking probes and sensors inside the waveguide. That's like trying to measure traffic by putting a giant pole in the middle of the highway. You end up changing the very thing you're trying to measure. Not great. Other methods are non-invasive. But they're either not very accurate, but they take a ridiculous amount of computer power and time. It's a classic headache. So this paper comes along with a super clever new idea. They say, let's not touch the waveguide at all. Instead, let's just look at the waves that come out the other end. They create a pattern in the distance in the Far-Field. And these researchers figured out how to analyze that pattern. They only measure the amplitude, which is the strength and intensity of the wave pattern, and project out one piece of information. They tried to reconstruct everything else, including the super tricky phase information. This is a famous problem called Large Retrieval, and it's notoriously difficult. It's like listening to a symphony, only hearing how loud it is. And from that, trying to figure out which instruments were playing and what notes they hit. Sounds impossible, right? But their secret weapon comes from the world of deep learning. They use an optimization algorithm called AdaMax, but with a special twist, a large step size strategy. Okay, so what does that mean? Imagine you're blindfolded and trying to find the lowest point in a hilly park. Most algorithms would take tiny, cautious shuffling steps. They move slowly and are very likely to get stuck in a small ditch, thinking it's the lowest point in the whole park. That's a local memory. But this method, it takes big confident leaps. It has enough momentum to jump right out of those small ditches and keep searching for the true lowest point, the global optimum. This lets us solve the puzzle way more effectively and avoid getting fooled by wrong answers. And this leads to one of the most fascinating parts of the paper, something they call ambiguity. This is so cool. They found that when you only look at the amplitude, there are always two possible answers for the phase that fit the data perfectly. You get the true, correct solution, and you get its near. The twin solution has all those same power levels for the modes. Other phases are flipped. So if in the true solution, wave A is slightly ahead of wave B, in the twin solution, wave B will be slightly ahead of wave A. The relative timing is mirrored. It's an inherent limitation. If you only look at the shadow, you can't be 100% sure which way the object is facing. And this is the brilliant part. They also show how to solve this ambiguity. You just need one tiny piece of extra information. If you know the real phase relationship of just one of the modes, like you know for a fact that wave A is leading wave B, You can instantly tell which of the two solutions is the real one and which is the twin. It's like a single clue that cracks the entire case. I just love that. Okay. So this is all very clever. But what does it mean for us in our daily lives? Where could this tech actually be used? First, and most obviously, high-speed communications. Internet is built on fiber optic cables, which are a type of waveguide. This technology could allow us to better analyze and control the signals inside those fibers, packing in more data and making our internet faster and more reliable. It's about getting more performance out of the infrastructure we already have. Second, let's think about how power systems. Things like industrial lasers for cutting and welding, even the massive microwave systems used in fusion energy research. They all rely on Waveguides to transmit enormous power. If the modes are messy, power is lost and the beam quality is terrible. This method could help design and tune these systems to be incredibly efficient and precise. We're talking about sharper laser cuts and more powerful, stable energy beams. And for a third one, let's get a little creative. Think about advanced audio technology. You could model a room as a sort of complex waveguide for sound waves, if you want to create super continuous beams of sound. Like the personal audio zones where only you can hear your music. You need to perfectly control the phase of the sound waves. This kind of phase retrieval math is a key step in making that a reality. Imagine your own personal sound bubble. That's the future listening. So how does this new method stack up against the competition? Well, the researchers did a direct comparison, and the results are honestly staggering. They measured the error, and their method had an error of around 225 times 10 to the minus 6. The computer method, it had an error of 2.6 times 10 to the minus 3. That might not sound like much, but that's a difference of 1,000 times. It's not just a little better, it's in a completely different league. This is where it gets even better. One of the older high-end methods took about 150 seconds to find a solution. Our method, running on a modern computer, can find the solution in about 13 seconds. That's more than 10 times faster. It's the difference between waiting for a pot of water to boil and just turning on the tap. This method is accurate, it's robust even with noise, and it's computationally cheap. It really seems to solve the trifecta problems that have plagued this field for years. So there you have it. We peek inside these complex wave systems without breaking them open. Using some clever math and a dash of deep learning inspiration. It's a huge step forward for everything from the internet to industrial manufacturing. What a fascinating find from the archives. That's all for today. Thanks for tuning in, and I'll catch you next time. Peace out.